if this is your function at the top, wherever I have an x, so notice how the x is the upper limit, you're going to let your upper limit become a 2. So the answer to this question is the integration of the graph of f, which is the graph you're given to work with, from 1 to 2. So if we go from 1 to 2, here's 1, here's 2, and it's been a while, but hopefully we are understanding the idea of an integral is the accumulation of change. When it's a graph, it's just the area. So if I just find the area from 1 to 2, so notice I have one complete square and then a half of a square, whatever that area adds up to be, that's the value of g of 2. So this would have to be 1.5. Okay. Same thing with number 2. If I'm going to have you go and find g of 5, that means since your upper limit is the x, the upper limit becomes 5. So we now want to integrate this graph from 1 to 5. So let me clean this up a little bit, because now I want to start at 1, but I want to finish up all the way over here at 5. So now we're doing this interval in there. If we go from 1 to 3, notice how we have a full 1, and then we have half and half, so this is 2. If I then go from 3 to 5, so I have to get over here to the 5, I have a 1 and 2 halves, so this is also 2. But since we're underneath the x-axis, if you recall, if we're just doing values, it's considered a negative value. So overall, this has a value of 0. All right. Jump to number 4 next, because number 4 is the easy one, easiest. Then we'll go back to number 3. G of 1 is now telling you let your upper limit, because that's the x, become a 1. And then it's a rule. It also should just make sense. If we're going to try to accumulate area from 1 to 1, we don't even have an interval to cover to accumulate area. We've talked about how if our limits ever end up being the same, our value has to be 0. Either way you think that through, that has to have a value of 0. Okay. Now go back to number 3. Not that this is hard, but it does require us to remember something else from last semester. Your upper limit is your x, so we're going to let that upper limit become a negative 2. G is always the integral of f from 1 to whatever x value we're trying to evaluate. And what we would then hopefully understand, and you don't necessarily have to do this, I just like doing this so that we're consistent in our method all the time, is we want that smaller number on the bottom, and we want the bigger number on top. If you didn't notice, that was not the case initially when we did that initial substitution. When we flip them, though, that requires us to multiply by a negative. So whatever the area accumulation is from a negative 2 to 1, we would want the opposite of whatever that value would be normally. All right, so let me clean this up. So where are we going? Negative 2 to 1. So here's negative 2 to a 1. So overall, that's 1, 2. This would have been 4. We would have gone from a negative 2 to a positive 1. We would have 4 complete squares if we added them all up. But since it is a negative of that, we would say that this value has a negative for overall. All right. So what this section gets at is the idea that the way I'm going to get the values of a certain function, in this case g, is by integrating a different function from 1 to whatever, to a fixed point to our variable point. Well, the next couple of things get into, if this is how I can find functional values, what if I wanted this thing's rate of change? What would the derivative of something like that be? So if I now ask you to take the derivative of this side, how in the world would that play out? What would that look like? What would we need to be able to do that? So we're going to hold off on 4 through 8 because you don't know how to do that yet. So that's the next section. So we're going to come back to these once we do the problem at the bottom of the paper. Another day, another year, I would probably try to explain this. This will sound like gibberish right now. We can cut through this a little bit quicker if we just go to the problems. So jump down to number 1, and then you can go back and look at that hopefully in due time, and it'll hopefully make some sense. So in number 1, the way I'm going to have you go through this and approach this question It's really a two-step order of operations idea. We want to take the derivative of this integral. So think of this as its own little problem, something that we were doing before break. We're going to do that first. So if I did the antiderivative of cosine, I would get the sine of t. And then we have to evaluate it from 1 to x. But keep in mind, as we are doing this, this little derivative is out in front waiting to do his thing. So he's waiting patiently. But whatever happens on the inside, we still have to take the derivative of at the end. Okay? So the next step, you plug in your upper limit, subtract, plug in your lower limit. And again, whatever we get on the inside at the end, this guy is still going to have the final say. We're going to take the derivative of whatever we get on the inside. We are now done on the inside because hopefully we understand sine of 1 is a number. Like if you could plug that into your calculator right now, if you had it handy, plug it in, it's going to give you a value. So what you're then going to do is now turn around and take the derivative of these. The derivative of sine of x gives us cosine of x minus, and then like I just mentioned, I don't know what sine of 1 is off the top of my head, but I think we all know I could do that in the calculator. It's going to give you a number of some sort. And we know the derivative of any number, regardless of what that number is, has to be a 0. So the only thing we would be left with as a final answer, get rid of this, would be the cosine of x. So if I go back to the top here at the very beginning of this problem, so I'm encouraging you now to go back up to here, what we just found is the answer to this original problem is the cosine of x. That's our answer. All right, so that's taking the derivative of that variable integral. All right, so number 2, let's go through the same thing. We're going to do the inside first, so just kind of an order of operations idea. So the antiderivative of 1 would be t, antiderivative of t cubed would be t to the 4th over 4, and then we want to evaluate that from 2 through x. And we are still currently ignoring the fact that we want the derivative of whatever we get on the inside. So I'm going to drop that down. Plug in your upper limit, so I would get x minus x to the 4th over a 4. Plug in your lower limit. And then do not worry about simplifying that, so just stop right there. When you get the 2 minus the 2 to the 4th over a 4, no need to clean that up. The reason there is no need to clean that up is because when I now turn around and take the derivative of all of that, the derivative of x would give me a 1. The derivative of x to the 4th over 4, you multiply by the 4, the 4s are going to cancel, should just give us an x cubed. The reason there was no need to clean this up is because isn't the derivative of 2 and 2 to the 4th, or whatever all that is, isn't that all going to have a derivative of 0? It's all going to go away. So that all we are left with is this as our answer. So if I now go back to the top, this is a room, kind of a room full of smart people, room / virtual room. What we just got this answer to be is 1 minus x cubed. All right, and then usually people start figuring this out, like, wait a minute, it's actually really easy. Why are we doing all of this work? At the heart, we're all the laziest people that we want to be to be successful. So if I look at number 3, and we don't want to go through all that work, is there a way we can say what that answer is right off the bat by just looking at numbers 1 and 2 and what happened in numbers 1 and 2? Okay, see some heads nodding yes, hopefully. What do you think, Shelby? You shook your head yes.
1 minus x cubed.
Good. So Shelby says 1 minus x cubed. I agree with her. If we went through all of those steps, I promise you, you're going to get that answer to be 1 minus x cubed if we went through those order of operations, antiderivative, derivative, all that good stuff. Okay? So what this is getting at, and we're going to talk about 4 and 5 here in a second because they're a little bit different, is if I take the derivative of an integral, Aren't those basically, and this is why basically the fundamental theorem of integral calculus, the idea that an integral or an antiderivative and a derivative are the opposite order of operations with each other, like a radical and a square, like an inverse sign and a regular sign. They're inverse operations, they undo each other. And that's ultimately, if we kind of look at what I have in bold here, all right, they're inverses of each other if we're continuous on a certain particular interval. And that's what's happening with all of these, so that we can do these very quickly. Now, number 4, do we think then, so what's happening ultimately, so here's what we kind of want to now show. The derivative and the integral are basically just canceling each other out, correct? And then all we are doing is taking whatever this variable limit is, and it's getting substituted in for the variable t. That's how every single one of these played out. This cancels, this just gets plugged in, and we get the cosine of x. Take this guy, plug it in for t. As these cancel, we get 1 minus t or x cubed. So if I now go to number 4, this should look a little bit different. Would this equal 1, or would we think this equals 1 minus x cubed? No, why not, Carter? You're shaking your head no.
It would turn negative because you're subtracting the constant minus the variable.
Good, that's a great answer, because that actually shows some understanding of this. So he's saying if we actually did this work, so you don't necessarily have to write this down. So if I did t to the 4th over a 4 here, from x to 5, what we would have plugged in this case is the 5. And then you would have subtracted the variable part of this. It's getting a little sloppy here. So as these become our 0, notice how we now get the negative out in front of what the original expression of 1 minus t cubed over 3. Now, I'm guessing most of you understood this because you saw the variable in your denominator. And that is the case. If our variable's in our denominator, those are going to get flipped. It's the same thing we would have done in the first 3, except it's going to be the negative of that. Okay, so good. All right, last one then, number 5, because number 5 is now the key to going back to the top of the page and be able to answer those questions. Because notice this is what we did at the top of the page. My function g was defined as the accumulation of change in f from some fixed point to some variable point. So g primed of x, write down what you think g primed of x should now equal. And then now see if this makes sense with your answer in number 5. The function I started with in number 1 wasn't the function I started with, the cosine, and didn't I finish with cosine? But it just became a function of x. The function 1 minus t cubed is the same function I ended with, but it just became a function of x. So the function is not changing. The variable at which we're finding the value of that function is changing. So when we come down here, we don't know what f is, but whatever f was at the beginning, it should have remained f, like that cosine remained a cosine. So f does not change, but this would have gotten substituted in. So this would now just be g primed of x is equal to f of x. All right, is that making sense? So don't flip the page, because now we're going to go at the top of the page and answer these questions. So if I now want you to do number 5, find g primed of 2. Notice how I left this blank here initially. We no longer now need to leave that blank. If I ask you what is the derivative of this function here, we now know the derivative of that. The derivative and the integral would have canceled. Whatever f would have been at the beginning would not change. It would ultimately end up being the same, but it now becomes a function of x. So go down here to number 5. If I want g primed of 2, wouldn't g primed of 2, if we understand this relationship up here, the statement of equality, doesn't g primed of 2 have to be the same as f of 2? This is the graph of f, if you recall. So f of 2, if we just look at that graph, doesn't f of 2 have a value of 1? Right, here's 2. Here's the functional value at that point. So g primed of 2, if g primed is the same as f, So let's actually label that because I like you to label these graphs. So now not only label this as f, but now say that this could also be defined as g primed. In this case, g prime is the same as f. They're equivalent to each other. So g primed of -2 is the same as f of -2. So we come over here, here's the graph of f. Over here at a -2, we have a value of 0. Everyone's thinking, that's pretty easy. It's kind of cool. Do number 7. See if we can put this together. Smart people, beginning of the week, should be fresh, rested. See what you think for g double primed of 3. Okay, anybody get -1 and would like to share how we get a -1? All right, Carter, what'd you do, Carter?
So if the rule of g prime of x is equal to f of x.
All right, so he said if g primed of x is equal to f of x, so he's looking at this, then what?
Since it's the double prime, you take f prime of x is equal, and then that should give you the answer. So if you do f prime of 3 at x is equal to 3, your derivative or the line tangent to the line is -1.
Good. So at the top here, he pointed to this first that I have starred, and then he just took the derivative of both sides, right? Like if I want g double prime, isn't g double prime the derivative of g prime? So we took the derivative of this equation, so that would take 1 tick marks to 2 tick marks. The derivative of f would have then produced f single prime, f primed. So if this is now an equivalent statement, then if I want g double primed of 3, that should be the same as f primed of 3. So we go back to 3, and since this is again f, the derivative means the slope of f. So this is just a line, so we really could just kind of do old algebra. Doesn't this always have a slope of a -1 in here? So at 3, our slope is a -1. That's where we get the -1 from. All right, good. Last one. So this should now be f primed of 1. Write down what you think that answer is going to be. All right. Isn't that now asking you for the slope of f? So the slope of f up here at 1. Do we have what's going on at 1? Should have an issue there, correct? Who is that? Yeah, Lily.
Sharp corner.
Good. There's a sharp corner there, so that means what, Lily? Good. That derivative value does not exist. All right. So f prime to 1, we would say does not exist. All right, good. All right, last thing I want to make sure we get through today at least. Go to the next page or whatever you have in front of you right now. I know what, like probably 3 different things going on. So in number 6, it said, did the limit that represented the constant matter in those previous questions? So when I went down here, notice how I deliberately gave you 1 minus t cubed, 1 minus t cubed, 1 minus t cubed. The constant here was a -3. The constant here was a 2. The constant here was a 5. Did that matter at all? Did that change our answer in any of these? No. So our answer there is no. And then the question is why? And it's just because the derivative of any constant is going to give us the 0. Sorry, when I write on Cami, it's not good. Derivative of any constant is 0. So that's why the constant limit didn't matter. So real quick, hopefully we can get these couple done in 4 minutes. It said, would straight substitution work for this? So what this means is, can we rely on this one here to say that this just cancels? And then we're just going to simply take the upper limit of x to the 4th and plug it in for t like we did in those previous problems on the previous page. Because if we do, then this would be our answer. So to answer that question, the answer is probably no, right? Otherwise, why would I be asking it? We're going to do, hopefully for the last time, we'll do this the long way. So the first thing you're going to do, we're going to take the derivative, and then I want you to go ahead, do the antiderivative of secant squared, so that's a tangent, of t from 1 to x to the 4th. Then, keep your derivative notation here, we still want that. Plug in the upper limit. Oops, I messed that up, don't copy that. In here. So tangent of x to the 4th minus the tangent of 1. And then we're done on the inside. There's nothing else we could do with this. So now we're ready to take the derivative. So when I now take the derivative of this, I would get a secant squared of x to the 4th, which is what we said the answer was if we just use our shortcut. However, shouldn't we also still have to do the chain rule and do the derivative of the inside and get a 4x cubed? All right, minus whatever, I don't know what the tangent of 1 is, but I do know it's a number, and the derivative of any number would be a 0, so then that's going to go away. So our final answer is actually not just secant squared of x to the 4th, it's 4x cubed times secant squared of x to the 4th. So we kind of got that, but we actually found that we should have a little 4x cubed out in front of this. So then the question is, do we have to do this the long way again? Or if we see something like this in the future, can we still just do the shortcut and then very, very quickly take this derivative, okay? And hopefully the answer is yes, because now all this adds in is whatever this guy's derivative is, you just got to multiply by that as well. The reason it was unnecessary in the previous page is because wouldn't the derivative of all of these x's just give us a 1, and it wouldn't have changed anything, all right? So real quick, because we can hopefully get a couple of these done. For number 8, all this is saying is these are going to cancel. We are going to take the x squared and plug it in for our t. So we do get a 1 over x squared, just like we did on the front page. But now what this is also saying is we also would have had to have multiplied by the derivative of x squared, which would be 2x. All right, we might stop there. I don't want to rush through too much. So we're going to fall behind today. Not shocking. So let's go ahead and we'll pick up from here tomorrow. There is an assignment that goes with all of this that I want to give you, but we'll hold off on it until tomorrow. So bring this tomorrow, and then we'll wrap it up and give you the assignment done. Okay? Okay. We'll see you guys. Have a good night. Shelby, that's right there why I hate covering homework from the night before.
You were close.
We were close.
Yeah?
Yes.